All right, now we're going to look at Hooke's law. Hooke's law is what we use for things that are flexible. Springs, rubber bands, things like this that follow Hooke's law. Now they all don't, but the ones that do, we get to apply Hooke's law to. Now Hooke's law comes in two varieties. One is a scalar function, which tells me the magnitude of the force is equal to K, which is the spring constant. This tells me how stiff something is. And X, this is the position, or how far it is stretched from an equilibrium. Okay. The second version is a vector equation, so this tells me that the force magnitude and direction is equal to negative kx. All this negative is telling me is that the force and the displacement are in opposite directions. So if I stretch a spring, its displacement is this way, but there's a restorative force from the spring back. And so you'll also see from time to time that this is given a subscript s to indicate that this is the force from the spring, not the applied force stretching the spring. Okay? And again, this negative sign is telling me it's a restoring force, meaning that the displacement and the force are in opposite directions. So let's see how we get to apply this into our typical force problems. So here I have an example that a spring was resting, hanging from the ceiling. I then attached a 200-gram mass and noted that it fell, or stretched the spring, I should say, 12 centimeters. And I want to figure out what is the spring constant of that spring. So the first thing I'm going to want to do is draw a free body diagram. And this has been reaching a new equilibrium. This block is not bouncing here. I've just hung the mass on it until it's stopped stretching the spring. So my free body diagram shows that I have mg acting down. I also have the force from the spring acting up. Now, I did say that it's not bouncing, so at this moment right here, I have a static equilibrium situation. So that means in my y direction, I have a first law problem, which tells me the sum of the forces equals 0. And so I have the force of the spring up minus mg, because it's down. Now notice I've already given the spring a direction. So what I'm going to use when I do this, when I've already given the direction to the spring's force, I'm going to use this version of Hooke's law, the magnitude of it, because I've already given it a direction. So here I have kx minus mg equals 0. And so now I can go ahead and solve for k. So let me just move this over here. So I'm going to move the mg over. So I have kx, and k is the spring constant. That's what I'm trying to find, is equal to mg. So k is equal to mg divided by x. So I will plug in my numbers. So I have a 200-gram mass, so I got to convert that to kilograms. So I have 0.2 times 9.8 divided by my displacement. How far from equilibrium has it been stretched? It's been stretched 12 centimeters, but I got to put that in meters, so 0.12. And so my spring constant comes out to be 16.3. Now the units for spring constants are newtons per meter. This can also be called an elastic constant, something like that. I usually just use the word spring constant. So if you do see it somewhere else as something different, it's the same thing. It's telling you about how elastic or how stretchy something is. The bigger the number, the stretchier it is. I'm sorry, the more rigid it is. The smaller the number, the easier it is to stretch. All right, there we go.